Okay, so now that we have learned about basically parallel and parallel and series resistors, now we need to talk about power. So basically, power, of course, in physics, if you read power in physics, it's going to give you a much more precise and concise definition of power in physics and what is meant by power in electrical circuits. But to put it in simple terms, basically, when you can say that when current flows through a resistor, it dissipates power, usually in form of heat. And basically, power is expressed in terms of what? So basically, then you can say that when current flows through a resistor, it dissipates power. It dissipates power, usually in the form of heat. In the form of heat. And well, the basically electrical power is expressed in terms of the unit. Basically, the unit for power is basically watts. And I suppose watt was the name of a scientist, a physicist or scientist. Now there is basically one fundamental formula for power, which is P. P is basically power. P is power, and this is the product of voltage versus current. Voltage versus current is power. And of course, basically we had V is equal to IR. We had V is equal to IR, the Ohm's law. So based on the Ohm's law, then you can say that if you can basically, okay, so over here in this formula, instead of V, for example, you can write IR. So P is equal to IR times I. Instead of V, I write basically simply IR. So then P is equal to I squared times R. That is another relationship that you can use for power. Or over here in the same formula, instead of I can write, basically, you know that I is equal to V to R. So instead of P, I can write basically V times R, which is equal to V squared to R. So P is also equal to V squared to R. So then we will get basically these three formulas for power, which is P is equal to VI, and also P is equal to I squared times R. Or you can say that P is equal to V squared by R. And in all of these three cases, no matter what sort of formula you use, the unit for power is watts, meaning that the power is expressed in terms of watts. Now, for example, if as an example you can for example calculate, if for example, now there is actually two things: the power that you calculate this way using V is equal to IR, or I squared times R, or which is also equal to V squared by R. What you need to understand about this is that you need to understand what is meant by this power over here, because usually we talk about power in terms of basically in two different contexts. So there is the power rating. There is the power rating of an electronic component, and you know that electronic components are, for example, resistors. You have basically you have batteries, you have basically transistors, you have, for example, vacuum tubes. And vacuum is one of those words I don't know how to write. I think WCW, vacuum tube. Okay, so CW, VACW. Okay, so you have vacuum tubes, for example, which is this. You have vacuum tubes. You have even I don't know, probably even a piece of wire could have some sort of power rating, and so on and so forth. So the power rating of an electronic component. Now, if you basically concentrate, for example, on a resistor, what you would get over there is that suppose that you have a resistor connected to a battery, and of course there is some V of S of your battery voltage, the power supply voltage, and the same voltage that you have over here you have on the two basically leads of your resistor as well. So V of S is the same V of S you have over here, and of course you have some R over here. There's some resistance related to this resistor, and then based on these two values, then you have some current going through your circuit. Now, what happens is that as a result of this V of S being present on the two leads of your resistor, and the current going through your resistor, current is going through your resistor in this manner, or in this direction. As a result of this V of S being present on the two leads of your resistor, and the current going through your resistor, there is some power dissipated in your resistor. And for example, suppose that, for example, the power dissipated here is 2 watts. Now, if the power rating of your resistor, for example, is 1/2 watt, what happens is that, of course, power means, in this context at least, it means heat being dissipated in your resistor. So this heat being dissipated in your resistor, of course, if your resistor is only 1/2 watt, that means that it's a very small resistor, and it cannot dissipate that much heat, that much of heat. And so after a short time, your resistor will simply fry. which is, of course, I mean, meaning that after a while your resistor is good for nothing. So then based on the nature of your circuit, basically you know how much voltage is going to be present on the two leads of your resistor in your circuit, and the current going through your circuit. You have to basically choose the proper rating for your electronic component, whatever that might be. It could be a transistor, it could be anything. And for example, in the case of a transistor, you have this basically, suppose that this is a transistor, and these two leads, for example, here you have your base, here you have your collector, and here you have your emitter, and here you have your emitter. Now usually what happens is that not much power, this is usually in transistors, this goes to ground, and this goes to some signal coming here, and some voltage coming in here, and then this basically and then you have basically what happens is that you have some load over here. You have some load over here that is connected to your power supplies. Let's say that this is your V of S, and negative, positive, for example. Your load is over here. Suppose that you want to turn a lamp on and off. So your lamp can go from here, can go to ground. Right here it can go to ground, and from here it needs to be connected to the positive pole of the power supply, and this is of course the negative pole of your power supply. So then here basically your transistor, the collector emitter junction of your transistor is just acting as a switch. Now of course in this circuit there is some voltage over here on the collector emitter junction of this transistor, which you can call V of CE, for example. V of CE, this voltage is there, and depending on how much current this lamp is drawing from the power supply, the same current is going through this emitter junction to the ground and going to the power supply, back and forth. So then what happens is that this V of C is present on your collector emitter junction, and this current is going through the emitter junction. So again, you have the problem of power over here, meaning that this voltage times this current going through the junction is going to basically specify the required power rating of this transistor. And that's basically, for example, that's basically why you, for specific tasks, you need a much bigger transistor on a heatsink, which can dissipate a whole lot of power. And if, for example, if all that you want to do is basically turn on some microcontroller chip or something that draws current in the range of, for example, a few milliamps or so, then you don't need that much of, you don't need a gigantic transistor with a whole lot of heatsink and all of those things, because of course then the emitter junction of the transistor is not going to have to dissipate that much of heat, and so you don't need the heatsink anymore. So basically, in short, you have basically two different things related to power. Basically related to power, basically you have two different concepts related together when it comes to power. There is the power which is dissipated on some, let's say on emitter junction of a transistor or on a resistor or something like that. And then there is the power dissipation rating of that electronic component. Both of those things have to match in order for the circuit to be running properly. That's important. Now you can, of course, we can then do a couple of calculations here to understand this a little bit. I mean, as long as the basically as long as the calculation is concerned, to understand that a little bit better. So we will go through a couple of examples here. Okay, so for example, let's say you have a voltage of 10 volts and a current of 3 amps going. This current is going through a resistor, and this voltage is present on the 2 leads of the resistor in some circuit, for example, as I showed you before. That happens. And so, for example, then in this case, your P is going to be equal to VI, which is equal to basically V times I, which is, and of course, in this formula that you have over here, your voltage has to be entered in volts, and your current is going to be has to be entered in amps. Otherwise, you will get a different. You will not get your power in watts. You would get it in, for example, milliwatts or megawatts or something like that. So you need to be careful about that. Of course, if you know what you're doing, then of course you enter your voltage and current in, for example, in millivolts and in microamps and so on and so forth, and then in the calculation you can figure out what your power is going to be. But otherwise, if you enter your voltage in volts, your current in amps, you're going to get your power in watts. That's basically how it works. So that's 10 volts times 3 amps, which is equal to basically 30 watts. 30 watts. So that's 30 watts. Or if your voltage is, for example, 100 volts and your current is basically 5 amps, then your power is going to be 100 times 5, which is equal to 500 watts. Or if your voltage is basically 120 volts, for example, and if your current is 10 amps, then your power is going to be 120 times 10, which is equal to 1200 watts, which is equal to 1.2 kilowatts. 1.2 kilowatts. So that's basically how you calculate power in a circuit, in a DC circuit, of course. And basically the formula that we talked about had other parts as well. So for example, suppose that you have a resistor of, your resistance is, for example, 20 ohms, and the current going through that resistor is 0.5 amps. So then you can calculate your power, as we said that P is equal to VI, and also I squared times R, and also V squared to R. So now you can use this part over here to calculate the power, meaning that you can write P is equal to I squared times R, which is equal to 0.5 squared times R, which is equal to 20, which is 0.25, which is equal to 0.25 times 20, which is equal to 500. 2 times 50, 502 decimal places, so that's 5 watts. That is 5 watts. If you have a resistor of 560 ohms, for example, 560 ohms, and if your current is 0.02 amps, then your power is going to be I squared R again. I squared R is going to be I squared times R, which is equal to basically 0.02 squared times 560, which is equal to 4, and then 4 decimal places, so 0.00 1, 2, 3, and 4 times 560, which is equal to 560 times 4 is equal to 0.242, 22, and then you have 4 decimal places, so that's 0.2240, which is equal to 0.224 watts. Or you can say, you can write this as 224 milliwatts. 224 milliwatts. If you have a voltage of 1 volt, and a resistance of 2 ohms, then we said that basically P was also equal to V squared to R. So V squared to R, so that's equal to 1 squared divided by 2, which is equal to 1/2 watt. Or if you have a voltage of 2 volts and a resistance of 10 ohms, then you have then P is equal to V squared to R, which is equal to basically 2 squared divided by 10, which is equal to 4/10, which is equal to 1/5, which is equal to 0.2 watts. Sorry, 4 to 10 is equal to 1/5. 1/5 is 0.4. 1 divided by 5, 0.2. P is equal to V squared to R, which is equal to 2 squared, which is equal to 4. 4 divided by 10 is equal to 2/5. I'm sorry, this is 2/5. This is 2/5. Now 1/5 is basically 1/5 is 0.2, so that is 0.4 watts. Okay. Now there is some other part over here. Let me read through this part. Let me see what that is. It says that resistors used in electronics generally are manufactured in standard values with regard to resistance and power rating. Quite often when a certain resistance value is needed in a circuit, you must choose the closest standard value. This is the case in several examples in this book. You must also choose a resistor with the power rating in mind, or place a resistor in a circuit that requires that resistor to dissipate much more power than its rating specifies. So basically what that means is that if you for example, if you need a 560 ohm resistor in some part of a circuit, so you need some resistance of 560 ohm in some part of a circuit. So there is always that resistor is always connected to something in the circuit, and there is always some voltage. There is always some voltage present on the two leads of the resistor, which you can call, for example, V of R, and there is always some current going through the resistor, which you can call I of R. Now this V of R times I of R is equal to the power dissipated in this resistor only. Now the power dissipation, of course, is going to happen in this resistor, meaning that this resistor is supposed to be capable of dissipating that much, basically that much power or that much heat. And what that means is that, of course, if it's not big enough, or if it's not basically, at any rate, if it's not capable of dissipating that much power, it's going to fry. So then, based on your calculation, when you know that the power dissipation in the resistor is going to be, for example, 1/2 watt, then of course you choose at least a 1/2 watt resistor, or even a little more than that, because you want to keep your resistor as cool as possible. You don't want your resistors to heat up. So and then of course you never choose a resistor. You never choose a resistor whose power rating is below this power dissipation which takes place in the resistor. So you need to be careful about that. And basically, resistors usually come in these packages, and there is basically this standard for the power dissipation capability of these resistors. There is usually 1/8 watt resistors, there is 1/4 watt resistors, there is 1/2 watt resistors, there is 1 watt resistors, there is 2 watt resistors, there is even, I don't know, even 10 watt resistors, and so on and so forth. So now you want to know, for example, in the example that we did before, you need to know what sort of resistor should be chosen for a circuit that basically, in the case of these examples that we calculated here, the first, for example, over here we had a 20 ohm, basically a 20 ohm resistor, and the current going through that was 0.5 amps, and we got the power dissipation was 5 watts. So then in that case, the resistor that you choose in this circuit has to be 5 watts or greater than that. A 5 watt resistor, basically it's a big chunk of resistor. Then, for example, in the case of this circuit, we got basically 224 milliwatts. So 224 milliwatt is something like of course it's 0.2 watt. So 0.2 watt is very close to, you have 1/8 watt, you have 1/4 watt. So 1/4 watt is basically 1/4 is the same thing as 0.10 divided by 40. Let me see. 1/4 is 0.25, right? 1/4 is 0.25. For example, if you choose a 1/4 watt resistor, that should be enough for this circuit, or even or greater than that, but not I mean, for example, for this circuit I would choose a 1/2 watt resistor or so. Now in the case of, for example, this circuit, we got basically 0.4 watts power dissipation. So that the resistor that you choose for this kind of circuit would be, for example, a 1/2 watt resistor or so, 0.5 or 1/2 watt resistor. And the resistor that you choose here would be I think there was some circuit over here. So that's a 1/2 watt resistor, for example, for this circuit. So that is basically that.